Hi everyone, I'm Roshan Ram with the data science team at IQT CosmiQ Works. In the next 15 to 20 minutes, I'll be walking you through how to use Solaris, our geospatial deep learning software package. So first, I'll be giving an introduction to Solaris and SpaceNet to set the context. Then we'll be looking at our use case or problem for today's setting. And then we'll look at the model architecture that we'll be implementing. And next, we'll go through a brief walkthrough of the code, and finally, we'll wrap up by analyzing the results. So what is Solaris? Solaris is, as I mentioned, a geospatial deep learning software package, which helps make a lot of the arduous and more involved processes of geospatial deep learning and machine learning a lot easier. So some of these non-trivial computer vision tasks include pre-processing images, which is way more involved than it might seem, tiling large format overhead images and vector labels, converting between geospatial raster and vector formats and other machine learning compatible formats, and performing semantic and instance segmentation, object detection, and other state-of-the-art related tasks using state-of-the-art deep learning models designed specifically for overhead image analysis, and also evaluating performance of deep learning model predictions. So the use case that we'll be looking at today is building footprint detection, which consists of three main pillars. First, we have pre-processing and what I like to call pre-processing. So in pre-processing, we pull the data, we organize our files well, and make sure that everything's set up the way it needs to be so that we can feed it into Solaris, our deep learning package. Then we have the standard pre-processing, which is necessary for any deep learning or machine learning pipeline. So in this area, we ensure images are tiled and processed as necessary. The second pillar is creating and training our models themselves. So in Solaris, this consists of the creation of CSV files so that Solaris knows where to pull images, masks, labels from, and where to store its outputs, and training masks, which are the labels. And we'll get into that in a bit. But the important thing to remember at this stage is that there are two main ways to go about using Solaris. One way is using the Solaris Python API, which trades off ease of use for flexibility. And the other way is using the CLI, or your native command line interface, which on Mac can be terminal and on Windows systems can be command prompt. So the CLI, your command line interface, is typically used for batch processing. And this trades off flexibility for ease of use. And the third pillar is testing and evaluating, also known as T&E. So in this stage, we'll be conducting inference, and which is actually seeing what outputs our model can produce, and converting to vector labels, which is just a human readable format for the images or outputs that we've produced. And at this stage, we'll also end up formatting our outputs for scoring, which we'll also get into later. So what is SpaceNet? SpaceNet is a nonprofit LLC managed by CosmiQ Works, dedicated to accelerating open source artificial intelligence applied research for geospatial applications, specifically foundational mapping. And these are some of our partners. So to date, we've had 6 SpaceNet challenges, and our 7th one has just been released. So today we'll be looking at the second SpaceNet challenge, building footprint detection. So this challenge, released in mid to late 2017, focused on data from 4 main cities: Las Vegas, Paris, Khartoum, and Shanghai. So the problem is building footprint detection, which, as you can see on the left, is basically we're given satellite images, overhead imagery, and we need to extract building footprint labels. So with over 850,000 labels for 7 geographical areas or regions, we'll be focusing on the Paris dataset of the 4 cities that were aforementioned. So what's the solution for this problem? Solaris. So we'll go about solving this problem in 4 main ways. First, we'll assess the data and pre-process the data. Then we'll prep by creating training masks and CSVs. And then we'll create the model and train our model. And finally, we'll implement our model and evaluate the outputs and compare them with our target or ground truth, our answers, basically. So let's walk through the model architecture that we'll be implementing. So we'll be using a top competitor, XDXD's model. XDXD used a UNet model, which is popular in computer vision nowadays. And he used a VGG16 encoder pre-trained on ImageNet. So this ended up being an effective building footprint detection model. So why did he use UNet? The UNet model was actually originally made for medical imagery and utilizes a technique known as upsampling instead of pooling, as is used with convolutional neural networks. So UNet consists of an encoder, a latent space, and a decoder. So XDXD basically replaced the encoder with another top performing encoder known as VGG16. And you can see some of the details of his model, the number of neural networks ensembled, his ensembling method, the pre-trained weights, which we discussed, and his training time, about 7 days. So on the left, we have UNet, and on the right, we can see the breakdown of VGG16. So one important thing to know as we're going through this process and eventually evaluating the results is we'll be using the SpaceNet metric to actually evaluate our results. So the SpaceNet metric is a coining for the IOU metric, which is an intersection over union metric, which basically says that the proposed polygon and ground truth polygon, if the IOU of those two entities is greater than 0.5, then we have a match. And from there, we can compute an F1 score. So basically what this is saying is we won't be penalized for partially detecting building footprints, but we will be penalized for completely missing a building footprint altogether. So once again, before we begin, the Solaris components and the workflow consist of first configuring our files and making sure that we've pre-processed the data and pre-processed the data. Then we have to create our model. And we have to ensure that we've created mass and CSV files so that Solaris knows where to pull the data from. Then we'll train our model, and finally we'll score and evaluate our model. So now let's do a code walkthrough and demo. So as you can see here, I have my data set up in a folder in a GPU. So here I have my testing data, and here I have my training data. And here is where I have the model file that we'll eventually be executing. So if we're starting from scratch, the first thing we'll need to do is import our data, import our libraries. So first we'll import Solaris, and then we'll import some of the other necessary libraries such as skimage, GeoPandas, Matplotlib, and Shapely. So the first thing we'll need to do, if it's not already provided to us, is create masks. So when we're given images, we're generally given images in TIFF files for the purposes of this demonstration. So TIFF files are basically an encoding of the image, and we'll need to create masks so that we know where the actual building footprints are within that image. We're given an image with building footprints from an overhead satellite view, but we want to know which parts of the image contain actual buildings. So to understand the truth or the answers to the training data, we'll need to create masks. So there are two ways to go about this. As I said before, we can use the Solaris Python API or use the command line interface. So first, let's look at how we can do this with the command line interface. So again, within the creation of masks under the command line interface, there are two ways to create masks. We can either do single mask creation, so create masks one at a time, or we can create masks in batches altogether. So there are a bunch of different parameters here, but we'll focus on the main ones. The main ones are source file, reference image, and output path. So the source file will be the original TIFF file that we take in, and this will be the file for which we want to find the answer, the file on which we want to overlay the mask. The reference image will be the geo-registered image, which will be in the same coordinate system, and we want to overlay this on our source file so that we know which parts of the image contain the building footprints. And the output path will tell us where we should store that combined image or the mask itself. So now if we want to create masks in batches using the Solaris CLI, we can use this command, make masks. We just pass in the batch parameter, and then we pass in an argument CSV. So what is this elusive argument CSV? So there are three columns to use when we're using batch processing in the Solaris CLI. We have the source file, the reference image, and the output path. So the source file, similar to the single mask creation with the Solaris CLI, will include all of the source files that you'll need to use under the source file column. The reference image will contain all the reference images respectively that you'll need to use under that column, and the same goes for the output paths. Now let's look at how we can do this with the Solaris Python API. So with the Solaris Python API, we have a function. This function is solaris.vector.mask.footprintmask. So under this function, we have a couple of parameters that will help us to do this. And here we can see we're reading in an image. And here we have the actual mask itself read from a GeoJSON file. So here's the TIFF file, once again, that's read in. And here is the GeoJSON file, which contains the truth values, where the actual building footprints are that we'll need to overlay on top of this. So if you can imagine this GeoJSON being physically overlaid on this image, this is how we'll do it using Solaris. So all we have to do is solaris.vector.mask.footprintmask, and then we pass in our GeoJSON and we pass in our reference image. And here we have our overlaid mask. So the next thing we'll need to do is create training CSVs and testing CSVs. Training CSVs will tell us from where we'll need to pull our training data. And so now we have masks, right? And now we have our training images. So we want to associate our training images to our masks. And to do that, we'll create a training CSV. So let's see how we can do that. So to create CSVs in Solaris, you have two options again. You can either use the solaris.utils.data.make_dataset CSV function, or you can create your own script to parse through your files and create a CSV. Originally, when I was doing this, I created my own script, but I found that using the Solaris function can be a lot easier. So there are a lot of parameters in this function as well, but the main ones that we need to focus on right now are image directory and image extension. So imdir will contain the path to the directory. So let's see what this would be in our case. So the image directory would be this, which, as if you can recall, this is where all my images are stored. Here we have the extension for TIFF files, because those are the types of files we'll be taking in. The stage at which we'll be using this function is the training stage first, and our label directory is called masks. And of course, we specify an output path where we want to store our output CSVs. So now the important part of this function is match_re. So match_re is a regex, or regular expression pattern, that helps us to extract substrings from the image and label files for matching. So if you're not familiar with regex, there are a lot of resources that you can use to learn how to extract substrings from larger strings. But in this case, let's take a look at what kind of files we have. So we'll go to the ps_rgb directory. And here we can see a variety of different files that were passed in as training data. So let's hone in on one in particular. Let's take a look at this one, sn2_buildings_train, and then we have some we have part of a string, and then finally we have image 156. So we see that all of these images have all of these files have one thing in common, a number. So if we want to sort masks, which might have the same name or maybe a similar name and have mask appended or prepended to them, then we'll want to focus on extracting the numbers from these strings. So the way to do that would be to use this particular regex pattern in this case. And the same thing would be done with the testing CSV, except the only difference is that we'd have to set stage equal to test and ensure that your output path is what you want is specified. So now that we've created our training CSVs, our testing CSVs, and our masks, now we'll just need to create the model. And the way we do this is by configuring a YAML file. So let's take a look at xdxd, the aforementioned competitor's YAML file. So this is the file that xdxd would have used if he was using Solaris for the SpaceNet 4 off-nadir challenge. But since we're focusing on SpaceNet 2, let's see how it stacks up in comparison. All right. So on the left, we have XDXD SpaceNet 4 YAML file, and on the right, we have the version that's been changed for SpaceNet 2. So there were only a few changes that really needed to be made to this file if you wanted to follow along. So first we see at the top, we have our model name. So I'll go through the parameters. First, we have our model name, which is known as xdxd_SpaceNet4. So what this does is it allows Solaris to go into its cache of all the different models weights and pull xdxd SpaceNet4 model weights. Then we have train and infer. So these are Boolean variables, true or false, which will tell us whether we want to train or infer at this point in time. If you set both of them to true, then then Solaris will run through the entire process and train as well as infer. And then here we have pre-trained equal to true because we're using XDXD's pre-trained model. Here you can set batch size, width and height of the images, and some other parameters which you can read up on in the documentation. But for now, the main parameters that are of interest to us are training data CSV and inference data CSV at the top here, at least. So here we can see that this is configured as path to trainingdf.csv. So we'll want to replace this with where we have our actual CSV stored, which, if you recall, is in Solaris test1 and training data CSV.csv. Same thing with inference data. So inference and testing are used interchangeably in Solaris, but they mean the same thing. So inference data CSV is where we've stored our testing data CSV, and you can see the path for that as well. So here we have a bunch of other augmentations, which allow us to pre-process and post-process our image. And here we have our training parameters. So our training parameters are what really allow us to tweak our model. And this section is particularly powerful because within less than 10 lines of human readable code, we're able to easily play with our model and create drastically different results. So here we can change epochs, as we can see here. It was at 60 in XDXD SpaceNet4 model. I changed it to 40 for the sake of training time. We have our optimizer learning rate, and here we have a model checkpoint file path and model destination path. So this is another important point to keep in mind. While you're training your model, if your model ever gets interrupted at any point in time, you'd want to have a backup of your model so that all of that training hadn't gone to waste. So what this model checkpoint parameter does is it will periodically, based on your checkpoint frequency, save your model to a specified location. So in this case, our specified location is GPU train models /xdxd best.path. And here we have a model destination path, and this is where the entire model will be saved at the end once the best result is generated. And here we also have an output directory, but note that this is under the inference parameter. So here we have training parameters, and here we have the inference parameters, and the output dir here is where our final model will be stored, where our final inference, will be stored. So once we've run our inference on all the testing parameters that we need to, our inference will be stored in GPU trained inference out. So now that we've configured our YAML file and created the model, we can train the model itself. So let's see how we can do that. So when we look at the documentation, we see that first we have to import Solaris, which is a standard procedure. Then we have config. So we use this function sol.utils.config.parse. So this is where we'll read in the YAML file that we just created, our actual model. And here, if you execute config, you can see that our model is pretty much exactly as we had entered it in. And here is the crucial step to actually train the model. We say trainer equals sols.nets.train.trainer, and we just pass in config, and then trainer.train. This line is literally all you need to do to run a geospatial ML deep learning model in Solaris. So with just 3 lines of code, you can train a state-of-the-art model. So now let's see what our results would look like for this model. So here we have the F1 score, precision, recall, false positives, false negatives, and true positives for a model. So we see with an F1 score of about 0.74, this model isn't doing too bad at all. So now let's actually see what our results will look like. So here on the left, we have a source image. Here in the middle, we have some predictions, and here on the right is our ground truth. So in the middle is what our model that we just created would produce. So from this image, we see that these are the building footprints that are extracted, and we can see that some rectangles are more sharp, whereas they're more gelatinous and blob-like in the middle. So if we continue to look at some more models, some more results, we can see that we see a similar pattern. So this might be what the 0.26 of the F1 score is unaccounted for. So analyzing the results, we see that about 79% of total predicted building footprints were picked up. So of those that are picked up, 79% are true positives. So that's what our precision tells us. We know that about 70 to 71% of true building footprints were picked up in predictions. That's what our recall tells us. And finally, our F1 score, which is a harmonic mean of precision and recall, which falls at about 0.7436, tells us that we have a pretty good model. So once again, we want to remember that these results are under the IOU metric, which means that we were penalized only for completely missing building footprints and not for only partially detecting building footprints. So once again, to recap, our Solaris components and workflow that we went through are: first, we pre-processed the data and we ensured that our data was set up in the files properly. Second, we created masks, which told us what the answers were for our training data. We knew where the building footprints were for our input images that we were training on. Then we created CSV files that we could pass into Solaris and tell Solaris where everything was placed. And finally, we trained the model in less than 3 lines of code. Then we scored our model and we looked at the results. So how does our model stack up against SpaceNet 2 challenge results? So if you recall, SpaceNet 2 was released in mid to late 2017. So our model had an F1 score of about 0.744 on Paris, which ranks up pretty closely to XDXD's Paris score of 0.745. Now, if we look at some of the other competitors, they had scores of 0.679 and 0.584. So to recap, we created a geospatial model with minimal code in a human readable YAML file. We trained a deep learning pipeline in less than 3 lines of code. And finally, we scored the model with less than 3 lines of code as well. So all of this is open source material, and if you're interested, you can find more at spacenet.ai. And if you're interested in the code and deploying Solaris yourself, you can find more info at github.com/cosmic/Solaris. And the documentation for Solaris is available at solaris.readthedocs.io as well, which can also be found at the Solaris GitHub. So if you're interested in more about Solaris, you can contact the SpaceNet Cosmic team or myself, and here are my socials. Thank you so much for listening, and I hope you guys have fun using Solaris.